Welcome to our notes on scatterplots, line of best fit, and correlation coefficient. Students will be able to identify the correlation and its strength given the scatterplot and its line of best fit. Students will also be able to interpret the line of best fit given a context to make predictions. Plot is a graph that shows the relationship between two variables. We will be focusing on linear scatterplots only for now. There are different types of correlation. Correlation only applies to a linear relationship between x and y. For any other pattern in a scatterplot, like an exponential or quadratic pattern, we will use the word association. All right, positive correlation. Graphs A and B below show a positive correlation. As x increases, the y's increase, producing a positive correlation this way. Same thing here. But this graph actually shows a stronger correlation than in graph A. Why? Because the data points are far closer to each other than in this one. Negative correlation. Graphs C and D below show a negative correlation. As x increases, y decreases. So you can see that here. Graph D has a stronger negative correlation than graph C because the data points are far closer to each other than in graph C. Graphs E and F show no correlation. That means there appear to be no linear relationship between x and y. In graph E, there is an association. It's quite circular, but since it's not a line, we will just call it an association, not a correlation. And here, the data points are so spread out that we can't see if a line should look like a positive one or a negative one or a flat one. It's just too spread out to make a determination that it's a linear relationship. Also, it's really important, correlation does not imply causation. If there is a correlation, we cannot assume that one variable causes the other variable because there are always other factors involved. So just be mindful when you're reading scatter plots. Yes, the data might suggest that x causes y, but that is not always the case. Line of best fit. A line of best fit is a straight line that best models data in a scatter plot. It allows us to make predictions and determine the type of correlation between two variables. The line of best fit should come as close as possible to every data point. Outliers can significantly impact the line of best fit. The line may go through all, some, or none of the points. Example 1. Which graph shows the line of best fit for the scatter plot? So let's look at A. Time watching TV versus grade is what's being plotted here. So we have some data points that are here. And it seems as though when time watching TV per week increases, the grade decreases, right? So our line of best fit should be a negative correlation, but the line that they put here is actually positive. So this one isn't going to work. All right, so we know that option A is not an option. So let's look at B. Our data set, like we said before, does have a negative correlation, but this line, while it does have a negative slope, which should go with the negative correlation, I would argue that this line is not very close to all of the data points. That's part of the criteria, right? So while it's following the trend, it's not really as close to all of the data points on the thing. So because of that, I'm going to go ahead and say no on this as well. Okay, we only have C and D left, and C is going to be our obvious answer here. But let's look at why D does not work. So here's D, and here's the line that they put here. We're looking for a line with a negative slope. This line has a 0 slope, which produces a flat line. That means that no matter how much time someone spends watching TV, their grade will be the same, a 50, no matter what. And that's not what the data is saying to us. So this is not an appropriate line of best fit. And so also I wouldn't say that this is no correlation. but it's neither positive nor negative. So if there is a data set that looks flat like this, it is just a correlation. I'm not really sure what the statisticians say about that, but we now know that D is not correct and C is. Notice that this line does have a negative slope, and it gets as close as possible to all of the data points. Unlike this one, it's close to some data points, but it's not close to the ones that are further away. All right, so this is probably the best thing it could do. And so that's what a line of best fit looks like. All right, so it does say justify your answer in a complete sentence. I used to. There were two things that helped me figure out which graph showed the line of best fit. One, the data shows a negative correlation, so the line should have a negative slope, right? So what that would do would be to eliminate A and D immediately because neither of those lines have a negative slope. But that leaves B and C. So you have to then distinguish the difference between B and C. So that's why I added a second sentence. The line in graph C also gets as close as possible to each data point, unlike graph B. And we said earlier that the line of best fit should come as close as possible to every data point. So just keep those two things in mind. Make sure that it's following the trend, positive, negative, or even flat, if that's what the data is showing, and make sure that the line of best fit is coming as close as possible to every data point. Recall that if a scatter plot has a pattern between X and Y, then it has an association. An association that is linear can be called a correlation. Before, we only identified whether a scatter plot has a correlation and how strong or weak it may be just from looking at it. But there's actually something that we use called the correlation coefficient, R, which is used to measure the strength of a bivariate data set. And don't get too, caught up on that word. Bi means two, variate refers to variables. So we're talking about a data set with two variables. That's all that means. We will not focus on calculating the R value in this course, but rather how we can use it to rank scatter plots from strongest to weakest. So if you were interested in taking a statistics course, you will learn how to calculate the R value by hand, but most people actually use programs to do it. So the R value ranges from -1 to 1. The closer to 1 or to -1, the stronger the correlation. The closer to 0, the weaker the correlation. All right, so let's look at all of these. So here is an R value of 1. Notice that if I were to draw a line of best fit, it will go through every single data point. So we will call that a perfect positive correlation. Okay, so if we decrease the R value just a little bit, 0.8 is still pretty close to 1. This is a pretty strong positive correlation. They say high positive correlation. I would say strong. Now, if we have 0.3, we're getting closer to 0, which has no correlation. 0.3, the data points are even more spread out. So it still shows a positive correlation, but it shows a weaker one. So here's a low positive correlation. And here is an R value of 0. There is no correlation. I don't know if the line is positive, negative, flat. It's just everything is all spread out. And now if we start going in the negative direction, right, the only difference between these two is that this one was positive, this one is negative. So it's still pretty weak or low. And then the data points get closer and closer together as our R value becomes -0.8. And so this is a stronger negative correlation or a high negative correlation. And lastly, if R is -1, that means all of those data points actually will fit on the line of best fit. And we call that a perfect negative correlation. Example 2, match the correlation coefficients with the scatter plots below. So if you wanted to pause the video so that you can see if you can do it yourself, I highly encourage that. So go ahead and pause the video if you want to try it for yourself. If not, just go ahead and hang on. And let's go ahead with this, shall we? All right, so I have these R values and I need to match them to the graphs A through F. And so what I'm going to do is I'm going to pick out the strongest ones first. So the strongest correlation coefficient is a positive one, and it happens to be 0.99. So I'm going to look for a super strong positive correlation. So this one has a positive correlation. In fact, I'm going to make notes for myself. This is positive. This looks negative. This is positive. This is negative. And then I don't know, this kind of looks positive for E, and F doesn't look positive at all. Let's just go ahead and work with what we have. The strongest positive correlation can be seen in graph C. So that must have the correlation of 0.99 because that is the closest to 1. Okay, so let's look at the next one. The next strongest would be R is a positive 0.9. So I'm looking for a stronger, like a less strong positive one than this one, but more strong than something else. So the only thing I see is graph A. So graph A is going to have this correlation coefficient here. All right, so there is another positive one, and it's getting really close to 0. Let's just hang on to that. I want to see a strong negative one. This is somewhat strong. It's a negative 0.85. And so out of these two negative ones, this one looks more strong than the other. Let's see. I'm just kind of estimating where this might be. I think this is a stronger negative correlation, so I'm going to go ahead and say that that's negative 0.85. I'm just going to make this a little bit thicker. Okay, and then a negative 0.4. This one might be it. Okay, so now we have the last two. R equals 0. F looks like it has no pattern whatsoever, and E kind of looks like it has a positive one. Like it could look like this. It's going in that direction, but it's quite weak. So I'm going to go ahead and write 0.5 for that one. All right, if you tried this on your own, see if you agree with what I have. If not, let's talk about it in class. All right, so here comes the core of this entire lesson. How do we use scatter plots and line of best fit to interpret information? So in order to do this, we must first find the equation of the line of best fit if it is not already given to us. Okay, so here's an example. It says the graph shows a line of best fit for data collected on the amount of a cell phone bill in relation to the number of minutes used. Part A, find the linear equation that matches the line of best fit. So the line of best fit is drawn in red here. And what we're going to do is we're going to ignore all of the data points, all the blue dots, because we don't use any of those dots to figure out the equation of the line of best fit. We try to find 2 points that are on this red line that we can read that go through corners. Okay, so I see 2 here. Let's see, let's go ahead and mark them up. Here's one, and here's another. Okay, now I'm going to write those 2 points here. That's 425. And the second one is 630. Okay, so you have to be extra careful here because I know that it's a pattern to like say how many you move up and how many to the right. You're going to move up. It's going to look like 1 up 1, right 2. So you might be tempted to say that the slope is 1/2. It is not, because look at your x scale. Your x scale is different than your y scale. For every X mark here, this one means 100, and then you have 200, 300, 400, 500, etc. But if you look at the Y scale, those numbers are very different. This tick mark actually represents 5, not 100. So this represents 100, but this represents 5. 10, 15, 20, etc. So you have to pay more attention to the distance between the two y values, 30 and 25, which is 5. And the way that you write that is change in y over the change in x. Okay, this is the same thing as me saying 30 minus 25. Okay, and then when I look at this horizontal distance, that's the change in x. So from 400 to 600, that's, given by this calculation. So 30 minus 25 is 5, and 600 minus 400 is 200. Okay, and I'm actually going to go ahead and simplify this. I know that 5 can go into both 5 and 200, so I'm going to show you divide both the top and the bottom by 5. So 5 divided by 5 is 1, and 200 divided by 5 is 40. That is my slope. Okay, so now we have to find the y-intercept. Now I can easily read that off of this particular graph. It's going to be 15, okay? But I want to show you how to find the y-intercept if you were only given these 2 points. Or maybe let's say you can't see the y-intercept on the graph. It's really important that we know how to do this. Okay, so we are working in slope-intercept form. Remember, slope-intercept form is y equals mx plus b. So far, what I have is y equals 1 over 40 x plus b. I found the slope. I just need to find my b value. What you do is you take any one of these points. I'm going to use this one because it's got more zeros involved. And I'm going to plug it in. So that 30 is my y value. And that 600 is my x value. Okay, now when you multiply fractions, this 600 is over 1. So I do this 1 times that 600, and I do this 40 times that invisible 1 there. Okay, so I end up with 30 equals 600 divided by 40 plus b. You can go ahead and use your calculator to figure this out, but I'm just going to look at this as if I didn't have one. All right, so I think about what is the largest number that goes into 640. The largest number that goes into 640 is in fact 40. Okay, and so 600 divided by 40 is 15. Okay, and then I'm going to subtract 15 from both sides. And voila, b equals 30 minus 15, which is 15. Okay, so it is confirmed that it is 15. Okay, now also just be mindful, sometimes the y-intercept might look like it's something, but it might be something slightly different. And so this is why calculating and doing your algebra is really important so that you're not like super off. Okay, part B says, what does the slope mean in context? Write a complete sentence. So first I want to remind you how to calculate the slope. It is the change in y over the change in x, or the change in vertical distance over the change in the horizontal distance. Okay, so we have a 1 up top, and the y values actually have units of dollars. Okay, so I'm going to write $1 up here. And then I have a 40 on the bottom. The x's actually have units of time in minutes. So I'm going to write minutes. And then I'm going to pause the video so I can write my sentence and then read it out loud. All right, so our slope is a positive 1 over 40, which means every 40 minutes used, the cell phone bill increases by $1. Now, this word increases comes out of the fact that the slope itself is positive. Okay, if the slope was negative, then we would use the word decrease there instead. And then what you do is you always talk about the bottom number and its units first, and then this one, okay, because remember x is the independent variable, and so the number of minutes doesn't depend on the cost of the bill, although some people might think about that. as far as how much they use their phone. But for now, the X is definitely the independent variable. So we want to say that for every 40 minutes used, the cell phone bill increases by $1. Part C, what does the y-intercept mean in context? Write a complete sentence. So if you want a more formulaic approach to writing a complete sentence, given any scatterplot content situation, you would simply read the point. The y-intercept is where x equals 0, right? And x is representing the number of minutes. So the y-intercept is 15, which means when 0 minutes are used, the cell phone bill is $15. Now, we don't normally talk like that. We would just say that the bill is $15 without using the cell phone or something like that. But this is a very formulaic approach to making sure you interpret what the y-intercept means. You could say when 0 minutes are used, that's the x value we're talking about, the cell phone bill is $15. That is the y-intercept in this case. Part D, how much would the cell phone bill be if 1,500 minutes were used or 1,500 minutes were used? Show all work and write a complete sentence. Okay, so we have the scatter plot here with all these different data points of, various customers using certain amount of minutes and having a certain bill. So what we did was we found the equation of the line of best fit so that we can make a prediction, right? It is not guaranteed that the bill will be this amount when we calculate it, okay? So one, we can't see it on this graph because 1,500 minutes is off of the graph somewhere, okay? We only see up to, 1,300 minutes. We can probably estimate what the bill will be. But we will have to use that equation that we found in order to answer this question. So we're going to go ahead and do that. Okay, so first things first, write the linear equation. Then substitute x for 1,500 since we're talking about minutes and that's the units of x. And then start simplifying. I ended up using a calculator. 37.5 is 1,500 divided by 40. And then I added that to 15. So 52.5 is what I get for the y value, which represents the cost of the bill. So the first thing you want to do whenever you're writing a complete sentence when you're talking about scatterplots is to say according to the line of best fit. Okay, that's only according to the line of best fit. Okay, because we use the line of best fit to make this prediction. And then you go ahead and say the cell phone bill will be $52.50 if 1,500 minutes were used. Okay, so remember the importance of saying this is to take into consideration that someone who, these two individuals talked around the same amount. They're probably anywhere from 250 to 300 minutes. But look at the difference in their bill, right? This one is surprisingly lower, even though they talked more. And this one is a bit higher, even though they talked a little less. So you can't tell a customer your bill will be $52.50. And then they get a bill that's different than that. I'm sure they would be happy if that bill was lower than that. But if their bill was higher, then they were not going to be very happy. So you're going to say, according to our calculations, your bill would roughly be about $52.50. And so this is the beauty of using statistics to make predictions about, things that may not have happened yet.